9 into 10 to the power 9. So finally you will get the formula 1 upon 4 pi epsilon naught q1 q2 divided by r square. Now limitations of the Coulomb's law. This law is valid only for the point charges. First, point charges. This law is valid only when 2 point charges are at rest. This law is valid only when 2 point charges are at rest. This law is valid when one of the point charges. This law is also valid. You can write here is also valid. Is also valid when one of the point charge is at rest and another charge is in motion, but the distance between them is fixed. I have given the example. Now you know. Earlier when we were discussing this, when I told you that, I think some other teacher told you this. So then you do not have the idea what is nucleus, and around nucleus electrons are revolving in a circular orbit. Now I told you, this is the atom. This is atom, and in atom we know nucleus at the center, and electron revolves around the nucleus in circular orbit. So basically this is a charge and this is also a charge, and this distance is not changing. So here you can apply the Coulomb's law. Numerical, for solving the numerical, what you have to do? Formula, some basic formula you should learn, like Coulomb's law you should know. How to apply the Coulomb's law. For example, we can just take one numerical, okay? Series numerical. 2 point charges are placed in air at a separation of d. 2 point charges are placed in air at separation d. Magnitude of both charges becomes 3 times. Then find the separation between charges if the force of interaction will remain same. So these are the two charges. They are separated by a distance d and they are placed in air. If nothing is mentioned, then you will consider air. And here air is given. So two charges are placed in air, separated by suppose distance d. Okay, so you can apply Coulomb's law first here. F is equal to k q1 q2 divided by d square. Now what you did after that, you have increased the magnitude of this charge and this charge to 3 times. So it will become 3q1, it will become 3q2, and distance, what will be this distance, so that the force between two charges will remain same. So again you will apply the Coulomb's law. K, this one, k q1 q2 divided by d1 square. And this force is equal to this force because force remaining same. So you can solve it. You will get the answer distance 3d. Means you have to separate the charges at a distance of 3 times of the initial distance, 3d. Okay, so in this way you can solve. So now dielectric constant or relative permittivity. What is that? Dielectric constant or relative permittivity is the ratio of the permittivity of the medium and the permittivity of the free space or vacuum or air. And this is also the ratio of force between two charges in air divided by the force between two charges in any other medium. And we have derived this also. We have taken two charges and applied the Coulomb law, and then when we will here these charges are placed in some medium. After that we will place these charges in some different medium, and there we will apply the Coulomb's law, and we will divide both the equation and we will get this. Okay, so basically k value, this you have to remember. Okay, k is epsilon m divided by epsilon naught is equal to f naught by fm. K is the dielectric constant, epsilon m is the relative, epsilon m is the permittivity of the medium, epsilon naught permittivity of the free space, f naught force in air or vacuum or free space, and fm is the force in any other medium. Okay, so this is another numerical video you can do. So you have to apply the Coulomb's law, okay, for solving the numericals. After that, I think there is no need of scalar quantities and vector quantities. already told you. So this is a vector. Now after that, we discussed the position vector and displacement vectors. Now right now I am not discussing it. Okay, this is the Coulomb's law in vector form. Okay, Coulomb's law in vector form. This is the derivation that you have to do. Okay, main things I will discuss. After that, the topic is the electric field. Okay, topic is the electric field. And what is electric field? Electric field means suppose a charge is there, and around that charge the region, that is the electric field. Electric field means space, the space around a charge in which another charge experiences the force. Suppose this is a charge, okay, and you are taking another charge. Suppose here is another charge, this is a test charge. So on this test charge there will be the force. There will be the force. Why? Because this is also a charge, this is also a charge. Either they will attract, either they will repel. Means on this charge, due to this charge, either there will be the force of attraction or repulsion, and that force per unit test charge is given by the electric field strength at that point. So definition you can write this, and strength of the electric field you can use this formula. Okay. And you can find force is this. So you can apply the Coulomb's law between this charge and this charge. Okay. And electric field is force divided by Q naught. Q naught is the test charge. Test charge means the charge which is experiencing the force due to this charge. And we are calculating the electric field due to this charge. So electric field will be KQ divided by R square. So what is the meaning of this? Suppose a charge Q is placed here, and at a distance of R from this charge, suppose there is a point P, and at this point P, the strength of the electric field will be given by KQ divided by R square. If suppose this is a charge and this distance becomes 2R, then what you will write? K into charge divided by 2R square. So it will become 2R square. Good. If charge is changed, suppose it will become 2Q, then here K into 2Q divided by 2R square. So electric field, this is the electric field strength at any point. In vector form, you can write electric field strength at any point. Okay, let me tell you once again. Okay, this is very easy. Suppose this is a charge, and here at this point you want to find the electric field strength, and which is at a distance R. So what you should do now? Assume here a positive test charge, and this test charge should be small, and calculate the force on this charge and divide this force by the charge itself, Q naught. So you will get the electric field strength value there, and electric field is a vector quantity, force is also a vector quantity. So this formula is there. There is one more way to define this. You can do that. Take force 1 and charge 1. You will get the unit electric field. After that, this is the equation of the electric field. E is equal to kq divided by r. So k is constant, q is charge is constant. So with distance, the electric field will decrease. If you will increase the distance, the electric field will decrease. So this type of graph you will get rectangular hyperbola. E is inversely proportional to 1 by r square. So electric field will also follow the inverse square law. And in vector form, you can write in this way: kq r square divided by r vector. R vector is the position vector of the point. So direction of the field. So direction of the field, for example, here, suppose this is a positive charge here, and at this point, we know now the value of the value at this point P. We know now the, suppose the distance is r. We know what will be the value of the electric field or electric field strength at this point. That will be k q divided by r square. So this is the magnitude. Now for direction, what you will do now? Here what I told you, assume here a positive charge and see the direction of force on that positive charge. So if you will assume here a positive charge, so this is also positive charge, this is also positive charge, both will repel. So the direction of the force will be in this direction, and direction of the electric field will also be in this direction. For example, suppose here is a negative charge. Here is a negative charge, suppose, and this is point P. Okay. So now I want the magnitude and the direction of the magnetic field at point P. So the magnitude will be kq by r square, and direction. Now direction, how you will calculate? This is a negative charge, so here you will assume a positive charge, I told you, and this is negative and this is positive, both will attract each other. So in this direction will be the direction of the force, and direction of the force is same as that of direction of electric field. So now Coulomb's law and electric field. Clear? We cannot cover all the topics, okay? Main topics I am covering. So this is the Coulomb's law. Coulomb's law. You should know what is Coulomb's law. And after that, the electric field you should also know. Okay, so Coulomb's law. What is the Coulomb's law? What is the force by the Coulomb's law? So you can define in this way: Q1, Q2 separated by a distance r in some medium or in air, you can say. So the force will be given by K Q1 Q2 divided by r square. And what is the value of K? 1/4 pi. If air is there, then you will use epsilon naught, otherwise you will use epsilon m. So if air is there, then epsilon m will become equal to epsilon naught. So K will become 1/4 pi epsilon naught. After that, I told you the electric field. So electric field definition, you can write the space around a charge in which another charge will experiences a force. Now, what is the value of the electric field? Suppose this is the charge Q, and this is a point A, which is at a distance of small r. So at point A, the value of the electric field is given by K into charge divided by r square. And for direction, what you will do? You will assume here a positive charge. So if this will be a positive charge, then both positive charge will repel. So direction of electric field will be same as that of force, and that this is the direction of the electric field here. And if this charge is negative, that in that case, the direction of the electric field will be in this direction. Superposition principle. So now neutral points. What is the meaning of neutral points in this chapter? Okay, neutral points.
Where there are like zero electric field.
Yeah, where the net electric field is equal to 0 due to any 2, 3, 4, 5, 6, 7, 8, 9 charges. So the point at which the electric field of individual charges cancel each other. Points of zero electric field. Neutral point means a point which is having zero electric field. For example, okay, one charge Q1 is there, another charge Q2 is there, and another charge Q3 is there. 3 charges are there, okay. So what is the meaning of the neutral point? So if here is the neutral point now, so at this neutral point, the value of the electric field will be 0. The value of electric field will be 0. E3, E2, E1 means at this point P, the electric field due to Q1, Q2, Q3 is equal to 0, and this point is known as the neutral point. Means you can say at point net electric field at point P will be the electric field due to charge 1. In vector I am writing electric field due to charge 2 plus electric field due to charge 3, and that is equal to 0. So points at which electric field of individual charges cancel each other. For example, if there are 2-point charges, 2-point charges are there, plus Q and minus Q, then neutral point will be somewhere here in between. Reason, if I will tell you the reason, it will take a lot of time. I mean, for each and everything, if I will tell you the reason, then it will take time. So I am giving just basic idea. So what you should do, suppose here you want to find, I am telling for this only, okay? For these points, you should try. This is plus Q charge and this is, okay. So I am telling for, okay, for this point. For 1 and 2, I will tell you. Neutral point is point where electric field is 0. So if there are 2 equal and opposite charges, equal and opposite charges, so the neutral point will be in between the charge, in the mid of the 2 charges. The reason is that here if you will find the electric field due to this charge, so that electric field will be in this direction. Suppose this is charge 1, this is charge number 2. So it will be in this direction E1, and due to charge 2, the electric field will be in this direction. And we know that electric field strength at any point is given by KQ divided by R square. KQ divided by R square. So now you can see here, this distance is same. This distance is same. Q charge, this magnitude of both the charges will same. So magnitude of E1 and E2 will be same. Equal and opposite magnitude in equal and opposite. These electric fields are equal and opposite, so they will cancel each other. So at this point, there will be no electric field. Now come to this. This is the equilateral triangle. This is the equilateral triangle. So in case of the equilateral triangle, this distance, and this distance will be equal. So at the centroid, you will get the neutral point. Why? Because due to this charge, the electric field will be in this direction. Due to this charge, the electric field will be in this direction. Due to this charge, the electric field will be in this direction. Now, if 3 vector and the angle between E1, E2, E3, E1, E2, and E3 will be 120 degree. This angle will also be 120 degree. This angle will also be 120 degree. This angle will also be 120 degree. If three equal vectors are at an angle of 120 degree, so they will cancel each other. So E1, E2, E3. So you can write the summation of E1 plus E2 plus E3 is equal to 0. So that is why net electric field at this point O is 0. So at the centroid, you will get the neutral point. If it is a square, at the center of the square, you will get the neutral point. If this is a hexagon, 1, 2, 3, 4, 1, 2, 3, 4. Pentagon is there. So at the center of the pentagon, this is a regular pentagon. Okay, regular means all sides of this pentagon are same. So at the center of the pentagon, you will get the neutral point. If there is a infinitely point charges are there, means you can consider this. If there is a uniformly distributed charge on a ring, you can say, then again you will get at the center the neutral point. Neutral point is the point where the electric field due to all individual charges becomes 0. Okay, if negative charge is there, then also this point will have the 0 electric field. Now this question is there. In this question, at A, B, C, D, 3 charges are placed. 1, 2, 3, 4 charges are placed, and this is a regular pentagon. Regular pentagon means all sides are equal. And they are asking the value of the electric field at this point. What they are asking? Electric field at this point they are asking. So we will use the concept of neutral point. This point will become neutral when this is the condition. When here equal charges are placed. Here equal charges are placed. And here also equal charge is placed, then at this point the electric field will become 0. Now we are considering, let's suppose plus q charge you have placed, so that here electric field will become 0. So electric field will become 0. Okay, when you will place a charge q here. So you can say that electric field due to all the charges at point O is 0. That is, electric field due to a charge placed at A, due to B, C, D, and E is equal to 0. This is equal to 0 now for regular pentagon. Now you can write this. Now you can find this value with the help of this value. Electric field due to a charge placed at Q, and this distance is A, because this become an equilateral triangle. This become A. So you can find this value and you will get this answer. So this value is KQ divided by A square. So this answer is KQ divided by A square. Neutral points clear? Neutral points are the points where the electric field due to individual charges is 0. Electric dipole. Again, electric dipole. Okay, just wait a minute. Okay. So electric dipole. Matthew, electric dipole, do you know? No,
So then when two equal and opposite charges are present in a system, they're known as dipole.
Yeah.
Yeah, they should also be separated by a distance.
Two equal and opposite charges separated by some distance. Example of electric dipole you can give as NaCl.
But sir, it's not an electric dipole. Right?
Yeah. Why? The reason I'm telling. NaCl is sodium chloride. So what is NaCl basically? In NaCl you have Na means sodium, and you have sodium atom and you have chlorine atom. This already existed in nature. So now, why we are saying this as a electric dipole? When you will break it, or when you will write in the ionic form, so it will become Na plus Cl negative. Okay. So what is the charge on N means? What is the meaning of Na plus? Na plus means Na is sodium is having charge of 1 electron. Means Na plus means you have removed 1 electron from this. You have removed 1 electron. So Cl negative means you have given 1 electron. You have given 1 electron means on chlorine there will be a charge equal to that of electron, and on sodium means Na positive means it will have a charge equal to that of proton. What is the atomic number of sodium? 11. So okay, let me tell you what is the
opposite charges, but how are they separated by a distance?
Yeah, you are right. I am telling why I am saying NaCl is equal and dipole, electric dipole. This is Na. In this Na, number of electrons, how many electrons are there? 11 electrons are there. And how many protons are there? 11 protons are there. Suppose you have removed 1 electron, so it will become Na positive. It will remove. It will have how many electrons now? It will have 10 electrons. 10 electrons it will have. Earlier it will have 11 electron and 11 proton. And how many protons are there? Protons will remain same, 11 protons. Now for this sodium ion, and one more thing we know that charge on electron and charge on proton is same. When you will add the whole charge, you will get finally what is the charge you will get? Plus E. Is it or not? Because on proton is having a charge of plus E, electron is having a charge of minus E. Okay, so you have 11 plus E, you have charge of 11 plus E, and you have charge of minus 10 E, so you will get only plus E. That is why you are getting, basically this is representing E positive, and this is separated by E negative. Na and Cl, these are the ions, and there will be very small distance in angstrom. Angstrom, you know, na? I told you nuclear fusion, very close, 10 to the power 10 meter. So basically, practical example of dipole is NaCl, Na positive ion, Cl negative. Basically these are two charges separated by some distance. And charge on this is Na charge of 1 electron, and on this also there is a charge of 1 electron. Equal and opposite charge. So charges are equal and opposite also. So electric dipole, system of two equal and opposite charges separated by small distance. So one more thing, this dipole, electric dipole moment. Now after that, electric dipole moment. So what is electric dipole moment? Suppose you should know, now you have the idea what is electric dipole. Two charges separated by small distance. Now we will discuss electric dipole moment. Electric dipole moment. So what is electric dipole moment? Take a dipole, and dipole is having two equal and opposite charges. So minus q is there and plus q is there. And suppose these two charges are separated by distance 2a. You can take this distance as a also, no problem. But in all the books, it is given as 2a. Okay. So take the distance as 2a. So dipole moment is given by the magnitude of the dipole moment is given by either of the charge multiplied by the distance between the two charges. That is q into 2a. And direction of the electric dipole is always from negative charge to the positive charge. So the electric dipole is having the magnitude also and is also having the direction also. So that is why this electric dipole moment is a vector quantity, and direction is from negative to positive charge, and SI unit is coulomb meter. So SI unit you can calculate from here. Unit of charge is coulomb, and this is distance. This is SI unit of distance is meter. This question, two charges are there separated by a distance of 6 micrometer. You can find the dipole moment. P is equal to q into 2a. So okay, after that the topic. So I think now electric dipole is some clear. So in this topic, basically this derivation may appear in the exam also. So this is the electric field on line of electric dipole. On the line of electric dipole. So basic idea I am giving you. First you should take one dipole. Basic idea I can give you how to calculate that. Okay, if I will calculate that, it will take much time. So first draw electric dipole. What you want to find? Electric field due to a electric dipole. Electric field on axial line of electric dipole. On axial line of electric dipole. Electric field on axial line of electric dipole. So draw electric dipole. Minus q charge plus q charge and separated by a distance of 2a. Fine. Now what is the axial line? What is the axial line? Axial line is this line. You can extend the line of the dipole. This is the line of the dipole. You can extend this. Okay. So basically this is the axial line. So on this line, they are asking the net electric field due to both the charges. Nothing is there. So you can take the point here or here or here, anywhere. So suppose you have taken the point here, P point. So at this P point, you should try to calculate the electric field. And how you will calculate the electric field? You know, suppose this is charge number 1. This is charge number 2. So at this point, you will find the value of E1 and E2. And you know the formula of the electric field. KQ divided by R square. Okay, so suppose due to this charge, okay, because this charge is negative, so what is the direction of electric field here? In this direction, E1. And due to this charge, the direction of electric field will be in this direction. So the net electric field will be E2 minus E1. If you know the vector addition, I told you that if two vectors are equal and are in the opposite direction, the resultant can be given by either E1 minus E2 or E2 minus E1. So in this way you can calculate. So this is the procedure, and here is the calculation done. Two charges minus Q plus Q separated by a distance of 2a. Here you want to find the electric field. So first you will find the value of E1, then E2, and then add these vectorically. Okay, and you will get this formula, 2 kp into r divided by r square minus a square to the square. And now what is r? R is the distance from the center of the dipole. Remember what is r? R is the distance from the center of the dipole, or you can say r is the distance between the center of the dipole and the point where you finding the electric field, net electric field of the dipole. One more derivation is there. Suppose here is minus q charge, means suppose a dipole is there, minus q and plus q, separated by a distance of 2a. So basically this is a dipole. This is a midpoint. This is a midpoint, means this distance is a and this distance is a. They can ask you the strength of the electric field or electric field at point A. Okay, and this angle is 90 degree. Basically A point is known as the equatorial point. So at this point also you can find the direction of the electric field. What you will do, due to this charge you will calculate the electric field there, and due to this charge you will calculate the electric field there. You will see the direction and you will add that vectorically and you will get the value. So how you will get the value? This is the point. Okay, so due to this negative charge at this point, the direction of the electric field will be in this direction. Suppose this is charge 1, this is charge 2, so it will be in this direction, that is E1. There will be some distance also, this distance you will take, and due to this positive charge now, the electric field direction will be in this direction. Suppose this is E2. Okay, now what you will do, you will join this, and this angle is theta. So accordingly you can get that this angle is theta, and accordingly you can, with the help of the vector, you can find the value of net electric field at this point. Okay, so next topic is this. You have to do the practice for this. Okay, basic things I am telling means how you should approach. How you should approach. So this formula you will get finally. And for the ideal dipole, R is much greater than A. So E equatorial you will get this Kp by R cube. Okay, and E axial you will get 2 Kp by R cube. Okay, Matthew and Fiza.
Yes, sir.
Yes, sir.
So after this, electric field lines. So basically, electric field lines are the imaginary lines, first of all. And electric field line shows the pattern of the electric field due to any charge or any system of charges. Pattern of the electric field means how the electric field is changing with distance. Electric field lines are simply imaginary lines. So next topic is the electric field lines. So geometrical and pictorial representation of electric field, you can say. Geometrical and pictorial representation of electric field, or you can say how the to show the pattern of the electric field, we draw the electric field line. Now, properties of electric field lines are very, very important. So we will discuss this. First property, very important. If some electric field line is there, and at any point of that electric field line, you want to find the direction of electric field, draw a tangent there. You will get the direction of electric field. This is the first property. Or you can say one of the property. Tangent to the electric field line give the direction of the electric field at that point. Suppose this is the electric field line. Electric field line is there. This is point number 1. This is point number 2. At point number 1, if you want to find the direction of the electric field, you will draw a tangent. At point 2, if you want to find the direction of the electric field, you will draw a tangent. Tangent, na? Okay. This is the electric field line. Suppose this is this type of electric field line you have. Okay. After that, these are 3 electric field lines. Okay. These are 3 electric field lines. So more closer will be the electric field line na, in any region. More will be the electric field strength will be there. So means, see these 3 electric field lines. 1, 2, 3 electric field lines are there. These electric field lines are closer at region 1 and they are far apart at region 2, means the electric field strength at this point 1 is greater. Okay. Now, if the electric field lines are supposed like this, so the distance between the electric field line, this electric field line and this electric field line and this electric field line, the distance is same. So if distance is same, so at any point in this region, the electric field will be same. Relative density means how close the electric field lines are there. Relative density of the field line is proportional to the strength of the electric field. Means more will be the density of the electric field. Okay. Okay. One more thing here. With example, we will try to understand each and everything. Okay. Statement. With example, we will understand. Suppose this is charge Q, this is charge 2Q, this is charge 3Q. Q, 2Q, 3Q. This 2Q is double of Q. This 3Q is triple of this Q. So, see how many electric field lines are there due to this charge, Matthew? Due to this charge, 2, na?
Yes, sir.
Two electric field lines. Now, if you will double the charge, na, see how many electric field lines? 4. Electric field lines becomes double. Now remove this. if you have a charge q, and suddenly or after that, if there is another charge 3q, 3 times of this charge, so number of electric field lines for this charge is 2. The charge is becoming 3 times, so number of electric field lines also becoming 3 times. Here the electric field lines are 2 and 3 times means 2 into 3, so 6 electric field lines should be there. 1 2 3 4 5 6. Okay, double the charge, double the electric field line, triple the charge, triple the electric field line, becomes 4 times the charge, becomes 4 times the electric field lines. So this will be clear. Number of field line depends upon the magnitude of charge. Third point, this is very famous from 10th class. 2 electric field lines can never intersect each other. 2 electric field lines can never intersect each other. Same as 2 magnetic field lines also can never intersect each other. Why? Because suppose these are 2 electric field lines. One electric field line, this is first electric field line, this is second electric field line. Choose any, suppose at this point B, these 2 electric field lines are intersecting. Now I am telling why these electric field lines cannot intersect. So what I told you in the first point, if any point, if you want to find the direction of the electric field, draw their tangent. Draw tangent at that point. So at this point, when you will draw the tangent now, so one tangent will be like this, another tangent will be on this line. So at one point you are getting 2 direction of electric field, 2 tangent you are getting. Can you get at one point 2 direction of electric field? No, that is not possible. So this is contradiction, and that is why 2 electric field line can never intersect. This is also very easy. Electric field line originate from positive charge and terminate at negative charge. Like in case of a magnet, what happens? Magnetic field line originate from the south pole or originate from the north pole and exit at the or terminate at the south pole. So here electric field line originate from the positive charge and terminate at the negative charge, like this. So electric field line can never form a closed loop. So this is very easy. For forming the closed loop, the electric field line should be like this. This is a positive charge and this is the electric field line emerging from the positive charge, and this is terminating again to the positive charge. Can the electric field line terminate at positive charge? No, because we know that electric field line start from the positive charge and end at the negative charge. But here, if this is the condition, suppose if this is a condition, then it should be like this, and this is not possible. Why? Because electric field line can not end at positive charge. Neutral point means the point where the electric field is zero. Neutral point is the point where the electric field is zero. if the electric field line are intersecting at the neutral point, means at neutral point there will be some electric field, and that is not possible. Another point, electric field lines cannot penetrate a conductor, and these field lines are perpendicular to the surface of conductor. This is the conductor, suppose this is a conductor na, through which the electric current can flow, conductor. So what will happen if this conductor you have placed in the electric field? So this type of pattern there will be. This is the electric field line, and inside the conductor no electric field line will be there, and after that this type of pattern you will get. And remember, the electric field line is perpendicular to the surface of the conductor. Field line cannot enter into the conductor. Okay. So remember this statement, field lines cannot enter into the conductor. I told you maybe I told you or not, electrostatic shielding. There is one topic, electrostatic shielding means if you suppose here is the electric field around me. Electric field is due to charges. For example, if there is a case of thunder, protect yourself from that lightning during thunderstorm. So what you should do, you should sit inside the conductor. If you will sit inside the conductor, the electric field inside the conductor is zero. Okay, the electric field due to that lightning will not affect you. Why? Because inside the conductor the electric field will become zero. Okay. This is the 6th point. So in 1 marks they can ask you this type of question. In reasoning they can ask you this question: why the electric field line can never form closed loop? So you should tell that electric field line starts from the positive charge and ends at the negative charge. That is why the electric field line can never form the closed loop. They can ask you why two electric field lines can never intersect each other. So what you will tell? At the point of intersection there can be two tangent. It means that there are two directions of the electric field at the point of intersection, and at one point there can be only one direction of electric field. So that is not possible condition. That is why they can give you like this. They can give you the one charge and they can give you another charge 4 times of the initial charge. And suppose they have given initially due to this charge there is only 2 electric field line, and another charge which is of 4 times of that charge. How many number of electric field lines, how many electric field lines will be there? So 4 times will be the electric field lines. Okay, now you know this. Closer will be the electric field lines, more will be the electric field strength. Now if they can give you this type of figure and they can ask you at which point the electric field strength is greater, at 1 point or at 2 points. So you have to think that at 1 point the electric field lines are closer, and at 2nd point the electric field lines are far apart. So you have to apply little of your brain also. This type of condition is given. So what you will do, you will see whether the lines are close or they are far apart, or the distance between the lines is remaining same. If the distance between the lines remaining same means electric field is uniform electric field, means same electric field everywhere. So draw electric field lines. So for an isolated positive charge means around this charge there are no other charges. There are no other charges. So we know that the electric field line originate from the positive charge. So electric field line due to a single positive charge or due to a positive charge will be like this. It will have a spherical symmetry, you can say. For negative charge, like this. Positive charge, the electric field lines are emerging. Negative charge, electric field lines are terminating or ending, you can say. Due to dipole, they can ask you this question. What is the electric field pattern due to the electric dipole? So this type of electric field pattern you will get. This is positive charge, this is negative charge. Electric field line will originate from positive to negative, positive to negative, positive to negative like this, positive to negative like this, like this, like this. You can join these two lines also. And on this line, you can draw a straight line like this. Because I told you this is the axial line, na? I told you at the axial line, the direction of electric field will be in this direction, in the opposite direction of the dipole. If two equal positive charge are there, so this type of pattern you will get. Neutral point will be here. Two unequal positive charges are there, so neutral point will be somewhere here. If Q2 is greater than Q1. Okay, if two positive charges are given, then neutral point will be here. Okay, another point. This is a conductor and this is a positive charge. So due to this system, how you will draw the electric field lines? So first you have to know here the electric field lines originate from positive charge. So electric field line will originate from positive charge. And here is a conductor. So electric field lines are perpendicular to the surface of the conductor. So it will be like this. And another point you have to remember, inside the conductor, no electric field lines, no electric field. So this, after that, you can draw the electric field line like this. One more way you can think of this. This is a positive charge, na? Due to the induction of charge, here is a negative charge induced on the surface of the conductor. So the electric field line will originate from positive charge and ends at the negative charge. Okay, move towards the negative charge. And these electric field lines are parallel to the conductor, and inside the conductor, no electric field lines. Here a negative charge is induced, but here a equal positive charge will be induced. So from here, the electric field lines are emerging. Okay, now suppose this end of the conductor you have earthed. Earthed means all the charge will flow through this wire to the earth, and this end will become neutral. So this type of pattern you will get. All the charge from here will go to the earth and no electric field line will be there due to this surface. This is the question in your board exam, I think. A metallic solid sphere is placed in uniform electric field as shown in figure. Which path is followed by lines of force? So can anyone tell me Matthew, Nafisa? Matthew and Nafisa.
4, right?
Correct. But why not 2 and 3?
Because it goes through
Yeah.
force only, excess.
Means why not 2? if suppose this question appeared in the exam, so what you will do? You will see line number 1. Okay, so leave that. Then you will see line number 2. You can see line number 2 is inside this conductor. So can electric field line be inside the conductor? No. So this 2 is not correct. 3 is also not correct. This is also inside the conductor. So now 4 is there and 1 is there. Basically, this is a sphere. This is a sphere. And one more thing you have to remember, if there is a sphere, center of the sphere will be there. Always remember, electric field lines are perpendicular to the surface. Perpendicular to the surface will be like this only. So it will be like this only. So this option. This is not the perpendicular. Perpendicular will always pass through the center. Okay, so this line should pass through the center. Okay. And this, why 1 is not correct? Because this one electric field line 1 is not passing through the center, or means not passing through the center means when you will join this line, it will be like this. But means this line number 1 is not perpendicular to the surface. When you will join it, it will pass from the center, means this line and this lines are perpendicular to the surface. Okay, so this another question. Why do the electric, we did this question in very detailed manner. I think, okay. Actually, I think there was another teacher who told you this topic. Okay. Why do electric field line not form closed loop? Just we did it. Yeah. So these are the questions that has already appeared in the exam. So I have not given these questions, already appeared in the exam. So first question, why do electrostatic field lines do not form closed loop? Just told you, plus charge like this, because electric field line originate from the positive charge and terminate to the negative charge. So this type of condition cannot form. Closed loop means close. Answer number 9. An electrostatic field line is a continuous curve, that is, a field line cannot sudden break. Why? Because you can write the formula of the electric field is this: E is equal to KQ by R square. So basically this function is continuous function. If you have a little knowledge of math, then you can apply here. The electric field function with respect to distance is continuous function, and continuous function does not have sudden breaks on all that. So the answer here written in different form, as the electric field and the electric force are continuous, so the change will experience, what is this? So the charge will experience the force continuously along the path. So this is also correct. That suppose they are saying that is, suppose the electric field is continuous. So if the charge will be here, the charge will be here. On the charge, there will be the continuous electric force and electric field. But I think this answer will be the more correct answer when you will write electric field function with respect to distance is a continuous function. At all the values, see, electric field formula is what? E is equal to KQ divided by R square. So at all values of R, it will give some value. At infinity, it will become 0. So that is why the range of it will be from minus infinity to plus infinity. Okay, so you can write this answer also. So this topic is quite important, I think. Should we move? Okay. So I am giving you idea how to revise all the things, and so what you should do now, the questions that are with topic. Okay. So all include those questions when you are revising. For example, when we were revising the properties of the electric field line. So obviously there will be some of the questions in your notes which is related to the properties of electric field line. At the same time, you should solve those questions. Okay. When you will solve those questions, the topic will become more clear. This is the way. Okay. After that, force on a charged particle in electric field. Force on a charged particle in electric field. This is the electric field. And this electric field is representing the uniform electric field. Means here, 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 here. Everywhere, the electric field is same. Okay. If suppose a charged particle is placed here, so on this charged particle, there will be the electric force in this direction. There will be the electric force in this direction due to the electric field. If the charged particle is positive charge, now, so force, direction of the force and direction of the electric field will be same. If charged particle is the negative charge, now, then direction of the electric field and the electric force will be opposite. Okay, Azan is going on, so we will wait for 1 minute. So on a negative charge, the force will be in the opposite direction of the electric field. On a positive charge, the force will be in the direction of the electric field. And this is a case of uniform electric field. Remember, uniform electric field. So on positive charge, it will be, and what is the magnitude of the force? This force will be the magnitude of the charge into electric field. This force value will be charged into electric field. This is the magnitude. If you want to write this in the vector form, then you can write force vector, charge is a scalar, and electric field is a vector. So in this form, you can write a vector is equal to Q into E vector. So this is for positive charge, this is for negative charge. So F is equal to QE, this is the magnitude. After that, here some mechanics will be involved. So to analyze that, on this charge, there is a force. Now it is clear. If the charge particle is in the electric field, on that charge particle, there will be a electric force. Means on charge particle, there will be a force also. There will be a force. And this charge particle 100% will have the mass also. Will have the mass. Means you can say on the mass there is a force. And if on the mass there is a force, means Newton's second law. There is a net force if there on the mass, then there will be the acceleration. Force is equal to mass into acceleration. Force is equal to mass into acceleration. Force is equal to mass into acceleration. And what is the force? QE. Mass into acceleration of the charge you will get from here. And this acceleration, charge is constant, electric field is constant, and mass is constant. You will get the uniform acceleration. And one more thing, if the body or the object to the charge is have the uniform acceleration, the equations of motion we can apply. Three equations of motions are there. P is equal to u plus at, s is equal to ut plus half at square, v square is equal to u square plus 2as. Okay, so one example we will take. For example, this is a charge, positive charge placed here, and this is the direction of the electric field. This is the direction of the electric field, and this electric field is the constant electric field, okay, because these lines are the parallel lines. These are the two plates. One plate is having positive charge, another plate is having negative charge. So electric field is like this. Okay. So now on this charge, what will be the direction of the force in this direction? This is a positive charge. So direction of the force, electric force, will be along the direction of the electric field. So in this direction it will be. And what is the magnitude? Q into E. Q into E. Okay, very good. Now, what is the magnitude of this force? In terms of mass, mass into acceleration. So ma is equal to E, and from here you will get the acceleration. So acceleration of this charge will be this. Now, if someone is asking, find the time taken by this charge to move from plate number 1 to plate number 2. So how you will do that? We have equations of motion. Initially, this charge particle will be at rest. Because you just place the charge particle there, and initially the charge particle is not having the speed or velocity. We have the acceleration, we do not have the initial velocity, but we have the displacement of this charge particle. When the charge part, no matter which path this charge particle is taking, suppose this charge particle is taking this path, or this path, or this path, 1, 2, or 3. Initially this charge particle is here, and finally this charge particle is here. So in case of 1, in case of 2, in case of 3, the displacement will be, what is displacement? Displacement is the straight line distance between the initial position and the final position. Okay, so displacement of this charge particle will remain d. Okay, displacement of this charge particle will remain d. Initially this charge particle is on this plate, and finally this charge particle is on this plate. So displacement we will take d. So you can apply second equation of motion. Matthew, do you know equations of motion? Have you little idea? Hello, Matthew? Hello? Oh, okay, fine. Fizia, do you have the idea of the equations of motion? Fine. So when you will apply the second equation of motion, s is equal to ut plus half at square, initial velocity is 0, time plus half, acceleration t square. So actually when charge particle will move from here to here to here to here, displacement will be different, but we are assuming that charge particle is just moving like this. It is moving because net force on this charge particle is in this direction. This charge particle will move straight in this direction. There is no other force on this charge particle. So this charge particle will move like this only. So initially this charge particle will be here. This is the initial position and this is the final position. Okay. So this is the displacement. And displacement is the straight line distance between the initial and the final position. So now you can put this value in this equation and you will get the time taken by this charge particle to move from one plate to the another plate. Mass of the proton. Basically here proton is taken, charge particle. So here initially this charge is at rest. Understanding, Hafiza?
Yes.
So in case of the suppose if there is a charge particle and this is the direction of the electric field, this charge particle will have the initial velocity also now. So this time now what will happen? This charge particle will follow this type of path because in this direction, this charge particle will try to move in this direction due to the energy of the charge particle and due to the force. This force will try to pull this charge particle in this direction. So basically combined path will be this. And in that case, we will calculate the L and Y by using the equations of motion. So we will take two axes, x-axis, y-axis. Along the x-axis, there is the initial velocity. And along the x-axis, the displacement is L. And there is no force along x-axis. Why? Because force on this charge particle will be along the y-axis in the direction of the electric field. Matthew, now it's fine.
Yes, sir.
Okay, now see. Once again, I am telling this is a bit complicated as compared to the other topic because here 11th class mechanics is involved. Little bit. Here, this is the one first plate. This is another plate. Two plates are like this. Parallel plates like this, like capacitor. Parallel plates are like this. This is negatively charged plate and this is positively charged plate. So due to these two plates, there will be the electric field. And electric field is from negative to positive. So this is the electric field. These white color lines are showing the electric field. You have put a charge on plate number 1. And you want to, and the distance between these two plates is D, that is given. And you have put the charge on the plate number 1 and you want to find in how much time this charge will move from plate 1 to plate 2, or will this charge will move from plate 1 to 2 or not? Okay, so what we will do, we know that whenever a charge particle is in the electric field, it will experience some force. So you have placed here a charge particle. Now on this charge particle, there will be a force. There will be a force, no? And this force will be the electric force. Means the charge particle will move. This is clear. And this charge particle will move in the straight line in this direction. Why? Because net force is along the electric field in this direction. So due to this force, we will calculate the acceleration. This. And then we will apply the second equation of motion and we will get the time. And after that, suppose if another condition, one plate, this is positively charged. This plate is positive charge, this plate is negatively charged. So electric field will be like this. A charge particle entered the electric field with the initial velocity V. Electric field is like in the upward direction and a charge particle is entered in the electric field. So what will happen now? Initially, the charge particle will have the kinetic energy. So due to that kinetic energy, the charge particle will move along the straight line direction. But there is another force in this direction. So what will happen? Charge particle is moving like this and force is moving like this. So the path of the charge particle will be like this. See, the charge particle will have the initial kinetic energy, and here is the electric field in the upward direction. So this charge particle is trying to move in the straight line due to the kinetic energy like this.
Yes.
But there is an additional force which is pulling up this charge particle. So due to the combined effect of forces, the charge particle will follow a curved path. Charge particle will follow this type of path, like this, like this, like this, like this, like this. So this type of path the charge particle will follow. Suppose charge particle follows this path and charge particle stopped here, covering the distance y, and the length of the plate is given as L. And this distance, total distance is D. Now here this becomes a two-dimensional motion. Do you know the projectile motion? Matthew, have you heard the name projectile motion? Suppose a ball is thrown from some building, and from the ground up, if a ball,
Yeah,
so that motion will
by like a projectile, like a ball or
a. Suppose a cricket ball, a batsman hits a cricket ball like this. So what will happen? The cricket ball will follow this type of path. So basically, this motion is two-dimension motion. Why this is two-dimension motion? Because two velocity components are there. Means there will be displacement in along x-axis also and along y-axis also. Means you can see two-dimension motion. The ball is moving like this. So now you can see x coordinate is changing or y coordinate is changing or not. Ball is going up, means y coordinate is changing. Ball is going towards the right, means y x coordinate is also changing. If two coordinates are changing, means that is the two-dimensional motion. So that is why this motion becomes two-dimensional. Why? Because x coordinate of this charge particle and y coordinate of the charge particle is changing. So for solving these kinds of problem, for solving two-dimensional motion problem, we will consider two axes, x-axis and y-axis. So this is the x-axis, this is the y-axis. So a length of the plate, and this is y-axis. So what we will do? We will see the motion. Now we will observe this motion with respect to axis. First with respect to x-axis, then with respect to y-axis. See what is in x-axis. So in x-axis, there is some initial velocity. In this is the x-axis, and length. What is the displacement in x-axis? L. Force in x-axis is 0. So if the force is 0, then acceleration is 0. Then what time it will take to reach this? If this charge is moving along the x-axis, then the time taken by the charge particle to reach from this plate to this plate will be time is equal to distance by speed. So t is equal to d L by v. Now in y-axis, initial velocity is 0. Displacement we have to find. There is a force Fy we can find charge into electric field, and from that force we can find the acceleration, and we can apply the second equation of motion. So this displacement we will get. Okay, here we will get 0 into t plus half into acceleration into time squared. So time we will get from here. We will put here, we will finally get this type of equation. Basically, this is the equation of parabola. The charge is constant, electric field is constant, this length is constant, mass is constant. This is the initial velocity, this is mass, this is charge, this is E. Actually, there should be the term of time. Basically, this is the equation, but here t should be there. Here should be t square. And this velocity, here this velocity is variable quantity. Okay, this velocity will change. Initially, there will be some other velocity here. Finally, means during this